welcome back. So, if you recall, we were discussing about photodetectors. In the last lecture, I had introduced the most important figures of merit for photodetector, and also we discussed a little bit on photoconductive photodetector, the differences of photodetectors with solar cells, although their operating principle is quite similar. Today I said we shall discuss about junction photodetectors, which are like PN junctions or Schottky junctions, very much like solar cell, with the difference that you may bias these photodetectors at an appropriate voltage depending on application. Photoconductor photodetectors, you have to apply bias. They are symmetric, IVs are symmetric with respect to y-axis. Junction photodetectors are like PN junction diodes like solar cells, which are not symmetric and which are vertical devices, P on top, N on bottom, or vice versa. I had also talked about metal semiconductor metal, MSM sort of a device which is lateral, very easy to fabricate, no doping is required in other things, and most people who publish research data, they initially do it on photodetectors based on MSM geometry. It's very easy to do that. So today we shall start with PN junction photodetectors, and we'll hopefully try to wrap up about the photodetector session so that we can start LED in the next class. Okay, so let's come to whiteboard again here. So what is remaining now is photodetectors that are based on junctions, or when I say junctions, it can be PN junctions. There is a variation of PN junction, it's called PIN junction or PIN photodiode, and then there is Schottky also. Okay, Schottky junction can be also used as a photodetector. I'm talking about the primary ones. A PIN actually is a PN junction in where there is an intrinsic layer between P and N. So I'll tell you about that. Okay, so we had just discussed PN junction as solar cell in the last class or so. If this is the Fermi level, I'm sure you have seen this hundreds of times probably, so there's nothing much new about here. Just I want to say that the same thing that I had told you in the solar cell class, you want the light to be predominantly absorbed in the depletion region, which is this, because the field is there. So any light that is absorbed that can give you rise to an electron and a hole here, the electron will be swept this side, hole will be swept this side. Okay, so the current will eventually flow in this direction, right? This area is actually this area is neutral or quasi neutral region, and here there is no field. So any photon that is absorbed here that gives rise to an electron hole pair is wasted, because that will neither drift, they will basically will diffuse and recombine and not contribute to electricity. Same thing applies here, except just what is also true in solar cell is also true here, that in one diffusion length over here and one diffusion length LP, Ln, sorry, here Ln, and this is Lp, in one diffusion length in the neutral region, if an electron or a hole comes, I mean because this is n-type region, so here if a minority hole comes somehow in this one diffusion length, then that hole can be swept away, and similarly one minority electron, if it comes within the one diffusion length, it can be swept away to this side, right. So that contributes to current. This is the depletion region, and of course this need not be silicon only, the band gap of the material will decide what wavelength of light you want to detect. Typically if you want to detect a light of wavelength lambda, you will go by hc by lambda, your Eg, hc by Eg has to be your band gap that you choose, so that the absorption is at band edge in order to get very sharp performance. But silicon can be used for all the wavelengths less than hc by 1.1 eV, which is close to 1100 nanometer, but it will not selectively absorb UV or visible, it will absorb everything from this nanometer. Okay. Now the thing is, this PN junction solar cells typically do not have a gain, because this N region and this P region, they act as blocking regions that do not allow the carriers to either drift or diffuse across this. So you can say that these are blocking regions, and so your gain inherently is 1, which means your photocurrent is actually your signal current, which is not the same in your photoconductive detector, if you recall, and this will be given by your efficiency times the optical power by hc by lambda. Actually this optical power times hc by lambda is something we call GOP in your solar cell. It's the same thing, it's per centimeter cube how many photons are there per second. Okay, actually this is the same thing. Okay, so this is the optical generation rate. Here I am writing it as a form of power by the wavelength, and you might recall that it's the same essentially junction, it's a junction one, right. So you will have the same sort of a IV, this is your IV, and this is your zero bias current. So even at 0 voltage you will get some current, and then it will slowly and eventually it will break down. So current is mostly flat. Slowly it might increase. If your sample is leaky, it might slowly increase, but that is okay. This is a dark current. This is a dark current, right? So you want this ratio, photo to dark ratio should be high for a better noise performance and so on, and eventually it will break down. Some people operate the device also near breakdown. At this point, just before breakdown, you can operate the device. In that cases, the gain is high, and those are called avalanche photodiodes. If you operate a PN junction or such a Schottky junction or other kind of photodiode near breakdown, just before breakdown, then what happens is that this breakdown is happening because of an avalanche multiplication. If you remember, there is a high field. This is a high voltage, no, high reverse bias. There is a high field in the depletion region. That high field will sweep the carrier so fast that the energetic carriers will knock off an electron hole pair, knock off an electron and create an electron hole pair. Those secondary electrons will again accelerate. They will create 2 more pairs and so on. That avalanche starts affecting at near breakdown. So just don't go to breakdown. Just before the breakdown, you bias the device and you operate the dark and photocurrent regime here. At that point, you can get some high gain. If you operate at such regime, it is called avalanche photodiodes. Avalanche photodiodes, and you might buy avalanche photodiodes also in market. They will tell you at what voltage you have to operate and so on. Okay, this can be of silicon, this can be of any material. Please remember, the material you will choose depending on the the light you want. I keep telling you that fiber optic communication or optical cables, fiber optic communication, typically the information is sent at 1550 nanometer. That is the wavelength at which the information is sent across the fiber optic cables. You will have these cables, no? There will be a core. There will be a core along which the light will propagate, and then there is a cladding layer. You can go through fiber optic textbooks and classes. Essentially, you have total internal reflection. Even if your cable bends, your light will total internally get reflected. Okay, and because the refractive indices are adjusted accordingly. So this fiber optic communication typically that brings you the broadband high speed internet, it's actually at 1550 nanometer. That is the wavelength, and the light is modulated very fast. If you say 1 Gbps, it means the light is modulating at 1 billion times per second. I told you there are many modulation schemes like frequency modulation, amplitude modulation, frequency shift keying, amplitude shift keying. These are signal processing things that you can talk about. I'll not go into that, but your modulation of the signal means 1 and 0, for example, and the output side and the other receiving side also you should be able to reproduce. So your detectors have to be very fast. For this 1550 nanometer optical fiber optic communication, the receiver will have a detector which is typically made of indium gallium arsenide. The mole fraction of indium and gallium will be tuned such that the band edge or the absorption will happen at 1.55 micron. This is the same thing as this, right? This is in-gas photodetector. In-gas pin diode can be used, and in-gas pin diode, which is just like a PN junction except that there is an I layer in between. I'll come to that very soon. These are commercially available. In-gas pin diodes are commercially available at these wavelengths, and even other wavelengths you can buy. So this is your junction, photovoltaic junction that you are using for detecting wavelength. And remember, if you use a PN junction like this with, for example, say indium gallium arsenide, you are going to get 1.55 micron absorption. It will also absorb all the wavelengths that are lower than wavelengths that are higher, lower than 1.55 micron, corresponding to energy of photons whose energy is higher than the band gap of in-gas. That is okay, but typically it is used at the band edge only. Similarly, if you take a PN junction of gallium nitride whose band gap is 3.4 eV, that corresponds to 365 nanometer, then this photodetector of gallium nitride will only respond to 365 nanometer or lower wavelengths, not higher wavelengths, because if you shine visible light, for example 400 nanometer is violet or 500 nanometer is green, all these light will be not absorbed in the gallium nitride wafer, a PN junction, because the band gap is larger than that of this energy of the photons, right? So anyways, this, unlike solar cell where the input spectra of the sun is fixed, if you remember, the sun spectra looks like this, no? That sun spectra is fixed, and you are going to harness the energy and deliver the power to a load. A photodetector does not have a mandate like that. A photodetector is not expected to deliver power. It is expected to detect as faint and weak signal it can. Okay, and that wavelength at which it has to detect depends on the band gap of the material you are using. There is no fixed input solar spectra sort of thing. So that's why those are the fundamental differences between solar cell and photodetector. Apart from the fact that solar cell has to have an inbuilt junction field, so it has to have like a PN junction sort of thing. But in a photodetector, you might apply bias also, so it can be a lateral device without any photovoltaic action. Now if you recall, I had drawn the circuit diagram for a solar cell. A solar cell is essentially like a, there will be you are shining light and you are generating electricity. So this is this, and then there is a load. I am not drawing the series and the shunt resistance. There is a load across which you are basically taking the output voltage, right. There is a load that around which you are taking the output voltage. This is your solar cell or photovoltaic mode, PV mode. In a photoconductive mode, which is PC mode, is a photoconductive, you might want to apply reverse bias. Okay, so you will have a light shining here also. This is light, and then you have a resistance, of course, same thing, but except that here you will have a reverse bias applied here, which will be, they'll be there, right. One important thing is that in case of solar cell, which is this, in case of solar cell, you don't need a bias voltage, right. No need for biasing yourself, it will forward bias itself based on the load resistance. So you don't have to bias, and the load resistance that you are using here is much large. It's much larger than the intrinsic resistance of the device, because you want to deliver power here. On the other hand, in a photoconductor, in a photodetector mode, your load resistance that you are using here is much smaller, because you do not want to unnecessarily drop power there. Okay, your internal resistance, Ri is the internal resistance of the device, actually is larger. Okay. So in photodetectors, speed is important. How fast you can actually on and off the photodetector from, the light falling can turn on and off the detector. In solar cell, speed is not important, right. Sunlight is there. Sunlight is not important. Sunlight is not going to be switched on and off in the day like so fast, millisecond or nanosecond. Sunlight is there, so you don't have to worry about the speed of solar cell. But in you have photodetector, you have to worry about the speed. Secondly, photodetectors are also noisier devices, because your intrinsic resistances are high. You have to talk about the noise floor, because the noise can severely limit the impact of the photodetector. You want to detect a faint signal, but in case of solar cell, the solar spectra is fixed. It's kilowatt per meter square. Their noise floor is not like that. So solar cells don't worry about noise. Noise is not relevant so much. Okay, noise is not important in solar cell, because solar cells are nothing to do with noise. There will be thermal resistances, there will be short noise, quantum fluctuations, they don't care. Solar cell is very high, the sun's intensity that is falling is kilowatt per meter square, right, per nanometer. So that is the solar spectra falling, the sunlight falling. You don't worry about the noise and all. But in case of photodetector, your signal can be very weak, coming from a distant star. For example, you want to do mid-IR astronomy or UV astronomy. The signals that come from deep space will be very faint, right. So you need to detect very faint signals, not like kilowatt per meter square. That's why noise is very important in photodetectors. Okay, the expression for corresponding output voltage in this thing is also like the open circuit voltage in a solar cell only, except that here the wavelength is not the wavelength corresponding to sunlight, but the source, maybe IR, maybe mid IR, maybe ultraviolet, whatever, but otherwise its expression is similar. It's just junction photovoltage only, 1 plus the photocurrent by the dark current. It's the same thing. Okay, nothing fancy. Photodetectors have very low dark current, they have very small load resistance and so on, right. In case of this junction photodetectors like a PN junction, when you have like a PN junction photodetector like this is the depletion region, you will operate it at either 0 volt or this is P, this is N. So you will either operate it at a 0 volt or a slightly more negative voltage like -2 volt or -3 volt or -1 volt, whatever. So this is a a junction photodetector, and there is a depletion layer. The speed of this detector, which is corresponding to the 3 dB bandwidth, remember 3 dB bandwidth from last class? Okay, you will remember it. It's actually how fast it can operate. What is the bandwidth in gigahertz or megahertz is given by 1 by 2 pi into square root of there is a time constant associated with RC delay, plus there is a time constant associated with transit delay, which is multiplied by 0.36 for some reason. Don't have to worry about that right now. Essentially this is your RC delay speed. I am talking about the speed. What are the delays? Okay, and this is your transit delay. What do I mean by that? The speed at which your detector can operate will depend on RC delay, because a photodetector will have parasitic resistances, series resistance, some parasitic capacitances will be there. This is a PN junction, so it of course has a capacitance. No, that capacitance is given by epsilon, not epsilon s the material, by W. W is the depletion layer. So if your depletion layer is large, then what will happen? Your capacitance will come down if your depletion is large. If your capacitance comes down, then your RC delay also comes down, which means your detector should become faster. Okay, this is a charging discharging delay associated with the photoconductor being a PN junction. So it's like a junction capacitance. If you recall, we had studied that. It's a PN junction which is which acts as a capacitor, and there will of course be resistances associated. So you have a charging discharging delay of the PN junction that gives rise to this RC delay, which does not matter in solar cell, but it definitely matters in photodetector. That is the RC delay. Then there is transit delay. Essentially an electron will take some time to go, a hole will take some time to go, but on an average you take electron taking a time from going from this point to this point. So what is the total time here? A hole being from here to here, what is the total time there? That's called transit time, because the electrons and holes have to physically move to the edge of the depletion region to get swept away, develop the process of sweeping them away. So there is a transit delay. Now if this depletion region W is larger, the transit time will become longer, because the electrons and holes have to travel longer now, and so your transit delay become longer, will lead to a slower device, but your larger depletion width will lead to a smaller RC delay. So there is a trade off. There is a trade off you have to play on the depletion width W. You cannot have the depletion width W very large, otherwise your transit delay will be so much that your device will become slow. You cannot have the depletion width very narrow, because your RC delay will become very large owing to a large capacitance, and you will again lose the speed. Also the depletion region is the region where you want all the photons to be absorbed. If your depletion region is narrow, then the fraction of photons you are absorbing will also be small, and so your efficiency also will come down. So there is a trade off that you have to play. Of course light will shine from here or from here, and that light you do not want that light to be absorbed in this useless region P. So you might want to use a heterostructure such that P is slightly wide band gap, so that it is not absorbing the light that is falling on the intrinsic region. Do you follow what I am telling you? I will come to that. Anyways, I was talking about 3 dB bandwidth here. So your 3 dB bandwidth, okay, in this will be in gigahertz or megahertz or whatever, will be equal to 1 by 2 pi square root of your RC delay, right, plus your transit time delay into some 0.36. It comes from some frequency response and other things. So that comes from that. So if this component is larger, then one component dominates. If this is larger, then your RC delay dominates, right? So it's all these things you have done, and the best delay will happen when this quantity is equal to this quantity, then your frequency will be the fastest. Okay, so those things you can understand there. Now you see both of these delays depends on W, and if you look at the band diagram again, this is your depletion region W. You see the depletion region W depends on the what? It depends on the reverse bias that you are applying. It depends on the reverse bias that you are applying. If the reverse bias is more, depletion will become larger, right? If your reverse bias is reduced, depletion will become smaller. So if the depletion with W changes with bias, then your delay and your speed in bandwidth in gigahertz or megahertz also will change with bias, which is not a good thing. Sometimes you might want to bias it at -2 volt, sometimes -1 volt. You do not want the speed to change so much, but it will change. So the solution is to go for a PIN diode. In a PIN diode, you use a highly doped P plus layer on top of an undoped layer, and this can be any material: silicon, gallium arsenide, gallium phosphide, perovskite can be doped, gallium nitride and whatever, okay, and you use a very highly N plus dope region. If this is the case, then what will happen, I'll show you now. So if you use a P plus I and N plus, this is called pin junction. What will happen is that you have this Fermi level, okay. The P plus is very highly doped, so the Fermi level will almost balance here. N plus is very highly doped, Fermi level will almost here, and depletion will not extend towards P and N. Whatever depletion is completely only dropping across the is dropping across the eye region. This is your, sorry, this is your, sorry, I am not a good drawing person. Okay, this is your eye region. So, this is your Fermi level. Okay, this is your eye region, and your depletion width is fixed at the thickness of the eye region. This is di. This thickness of the eye region is the depletion. Your depletion width will not change. This will not change with applied reverse bias here. No matter what you apply here, your reverse bias thickness, your depletion thickness will not change, because this side is P plus, so depletion cannot go to P plus. This side is N plus, so depletion cannot go to N plus. It's very highly doped. You remember, if you have very high doping, depletion will not extend there. So your depletion has to be on the eye, which means your depletion region thickness is now fixed. If your depletion region thickness is fixed, then your transit capacitance RC delay time and your transit time delays are also fixed, which means your 3 dB frequency or your bandwidth is also fixed. So that's a flexibility you have, and that's why people go for PIN diodes only now. Your capacitance also is fixed, right? So that is a good time. So advantage of PIN is that your quantum efficiency also depends, by the way, on 1 minus exponential of minus alpha times the depletion where you are absorbing. In a normal PN junction, this depletion keeps changing with bias. So you do not know what efficiency you are going to get at minus 2 volt, minus 3 to calculate. But in PIN, depletion doesn't change. It is fixed at di, which is the thickness of the eye region. So your efficiency can be fixed. So in terms of designing your quantum efficiency, hence responsivity, hence your 3 dB frequency and so on, speed and bandwidth and so on, your PIN device will definitely be better compared to your PN devices, because you can fix these numbers beforehand. You can design these numbers better. Okay, that's why you use that. And I also told you that sometimes you might want to use a slightly higher bandgap material, so that if you have your Fermi level like that, you might want to use a slightly higher bandgap material, So what will happen is that this is P plus and this is N minus. Your bandgap on the P side is slightly bigger than on the I side. Bandgap on the N side also is slightly bigger than the I side. So any photons that are coming here, these are H nu photons. These photons that correspond to the bandgap here will not get absorbed here, because this is a wider bandgap. So all the photons that are shining that correspond to the bandgap in the intrinsic layer will definitely pass through very easily. It will not get absorbed in the P type layer or N type layer, which will not lead to any useless waste of the carriers. So these are slightly heterojunction photodetectors are also used. There are advantages and disadvantages also, of course, in any case. And similarly, you have this Schottky junction photodetectors, which is the same as PN junction, except that these are Schottky. So you have something like, say, metal work function, and then you have a barrier like this, right? So if you shine light from the top, then in this depletion region, whatever is absorbed will immediately go this way and that way. Of course, most of this will get absorbed in a near the surface. We don't talk about holes so much, we talk only about electrons, and because only electrons go on transit here, so these Schottky detectors can be quite fast, because anywhere that you have only electron transport and not hole transport, the device tends to become faster. So Schottky device also is very similar to PN junction device in terms of operation, speed and all these things. So you don't have to worry, Schottky junctions are also used, but the dark current in Schottky junction will not be as good or as low as PIN junction, because reverse leakage in Schottky junction, from your earlier classes, reverse leakage in Schottky is always higher than in higher than leakage in what? PN junction. Remember, of the same material, I am talking about same material. You cannot compare Schottky junction of gallium nitride with PN junction of silicon. Talking about the same material. In PN junction, the barrier, the dark current ka barrier goes as e to the power minus Eg, the band gap by kT. In Schottky, the barrier, the leakage current goes as e to the power minus Schottky barrier by kT. Schottky barrier is this. A Schottky barrier will never be as big as a PN junction and the band gap. So your leakage in the Schottky junction is slightly higher. You can get faster devices but little noisier. So depends on the application that you are looking at, you can go do that. Okay. So I told you different materials are used for photodetectors. For this near IR photo detection, the near IR wavelength stretches from just after human eye sensitivity ends at around 700. So from around 0.8 micron to maybe around 2 micron. The definition can slightly vary depending on whom you are talking to. And then mid IR stretches typically from 2 to 5 micron. Sometimes people also have a slightly different range. And then you have far IR. Far IR will go from like 5 micron to much more, maybe 12 micron or more. Even sometimes people call it 8 micron and 12 micron. These are the ranges. You have to go to progressively lower and lower bandgap materials. Mid IR, for example, detectors. Mid IR detectors have extremely high importance in military surveillance, in night vision, in tactical and strategic things like in airport security. If you do an mid IR imaging, you will be able to see who has a concealed weapon. You can also detect very dangerous gases. In the night time you can see enemy movement. So mid IR detectors are very strategically important, and that's why import of mid IR detector is very restricted, and it's purely military, a lot of security related things. Besides that, mid IR detectors can also detect things like some skin cancer and tissues and cells and all. So these are very important and promising devices. Far IR is also very important for many of these industrial waste monitoring and other things. There is always a black body radiation. Human body temperature is around 98 degree Fahrenheit, 98.4 degree Fahrenheit, or around say 37 degrees Celsius. 37 degrees Celsius is the human body temperature. Everything that is at a finite temperature emits a black body radiation. No, so human body, Wien's displacement law. You have learned about Wien's displacement law. You can find out what is the wavelength at which human bodies at normal temperature will emit. It will emit at around, I guess, 10 micron or 10 point something micron. That is the wavelength of mid IR, far IR infrared signature of human beings, animals also, depending on the temperature. So if you have these far IR detectors, you can detect all these things. So there's a lot of applications. Of course, these devices have to be cooled down. Not only the devices, the entire lens, the electronics, everything has to be cooled down, because if you consider the band gap will be like 0.1 eV, 0.05 eV. So the room temperature thermal energy is so high, 26 millielectron volt, that the probability of this thermal excitation generating carriers in this material is very high. So your dark current is ridiculously high. You will not be able to differentiate the signal from a noise. So that's why you cool down, so that KT becomes very low, 77 Kelvin, 50 Kelvin, 4 Kelvin. Your system becomes so cool that your KT becomes lower, and compared to KT, this signal will now be bigger. So you cannot get, the noise will come down. So this is one form of idea. So these mid IR and IR detectors are very important for a lot of applications, military and strategic. Visible detectors also can build. Silicon can do most of the visible detection if you want. Our human eye also detects visible. Of course, the magnitude of the light that you can detect with photo detectors, you can make it much more sensitive than the human eye. And also there is UV detectors for many other applications and other things. Okay, so these are different categories of UV detectors, applications of various detectors that are there. Mid IR and IR detectors are a large number of applications. Please remember that, apart from these things also. Okay, so we shall end up our lecture here today. Now we are done with photo detectors. We have finished the photo detectors discussion. The various categories of detectors I have briefly discussed about, also the speed, about how fast you can operate a junction photo detector. There are two limiting factors. One is that there is an RC delay because of the capacitance charging. One is the transit delay that electrons and holes have to take to reach each other in the other ends. So both of the delays matter in deciding how fast the detector can operate. If you want to operate at a 1 gigahertz, for example, the delay has to be less than a nanosecond, for example, right? So all these things are important in designing photo detectors. Heterojunction photo detectors are there, avalanche photo detectors are there when you operate at near gain. Photo detectors are a vast topic again, like any other topics, BJTs, MOSFET and all. Within this syllabus, we cannot do justice to a lot of these things. Each of the topics in photo detectors can cover many lectures. For example, in avalanche photo detector itself, there are so many things to understand in terms of gain, noise and bandwidth. Okay, the trade-off. There is something called SAM, separate avalanche multiplication photodiodes, the kind of epitaxial design that you can do for enhancing the gain. There are so many threads that you can discuss about, even in terms of speed and other things. Okay, there is also QIP, quantum well infrared photo detector, mercury cadmium detector, and so many detectors are there. You can definitely read up, discuss with me and other things over email, but here in the course we will only restrict ourselves to whatever we have discussed till now. Okay, so we shall end up photo detectors here. From next class we shall start with light emission, which is LED. Okay, so thank you for your time.